So last time we did one exercise in which we showed that first quantization and second quantization give the same result. We did it explicitly for the one-body operator, okay? So when you have an operator that is expressed in first quantization as sum over all particles of some operator that depend on the particle I only, you call this one body. And we show that in second quantization, if you select any arbitrary basis alpha, then the expression for u is the following. Or better, sum over alpha and alpha prime u alpha, a dagger alpha prime a alpha. Okay? So in general, it's a double sum on the labels. There is one a dagger and one a, okay, with in general two indices, alpha prime and alpha. And for the given choice of alpha prime and alpha, there is a matrix element of this object, a single one. Don't put the sum, okay? Just a single operator in between the two states. Okay, so let's give an example. Suppose that this was pi square over 2m minus z e square over ri, just to exemplify the potential due to the nucleus. Or in general, in a crystal, this could be pi square over 2m plus the potential due to the lattice, okay? So the lattice potential Ri, okay? This is also one body, okay? So anything like this, in general, is treated in this way. Notice, here I have a matrix element, and in general, this state here has an orbital part, okay, and a spin part, if you remember, okay? So there is this, how did we call it? Sigma alpha, okay, something like this. So orbital and spin. Many of the operators we are considering here do actually not depend on the spin explicitly. There is some of them, okay? For instance, this. In that case, the spin in those two states match up exactly, okay? In other words, the spin there and the spin there should be the same, okay? So for instance, if I make it explicit, the spin, then I should write something like sum over the spin, sum over the alpha and alpha prime, only the orbital part of the quantum numbers. Then I have the orbital part of the state, the operator, the orbital part of the state, and then I have a dagger alpha prime sigma a alpha sigma. In other words, the spin is conserved, okay? It's not changed by the operator, okay? So the spin which you destroy and the spin of the particle you create are the same, okay? Is this clear? Obviously, there are cases, okay, of one-body operator that involve the spin, and in that case, you should be aware of the fact that, in principle, the spin might change. Okay? Is this clear? Good. We proved explicitly. In fact, we proved it in two steps by first selecting a basis of eigenfunctions of u, and then moving to a general basis, that this gives exactly the same matrix element of this when calculating between two arbitrary states, alpha 1, alpha n, and alpha 1 prime, alpha n prime, okay? Where the states here are the correctly symmetrized states, which are a basis of the many particle Hilbert space. In second quantization, they look particularly simple. They are just a dagger alpha 1, a dagger alpha n acting on the vacuum, okay? In first quantization, they have a more clumsy look of this type, sum over all permutations, well, C to the P, the permutation acting on alpha 1, alpha n. Okay? Then we also argued, although I didn't do the algebra explicitly to the last thing, that if you have a two-body operator, which is the other part which is very important, because typically Hamiltonian of many body systems have one-body terms and two-body terms related to interactions. Okay? So both are very physically relevant. So for instance, in first quantization, a Coulomb potential, something like this, or any other form of interaction potential, so something like sum over I different from J, 1/2 some V, which depends, for instance, on Ri and Rj. This potential might be more complicated than just a Coulomb one. For instance, two helium atoms interact not with a Coulomb potential, but with a potential that looks pretty much like a Lennard-Jones, okay? Although it's a bit modified. People have studied a lot how to describe the potential of helium, for instance, because it's a very important system on which very sophisticated experiments have been performed, okay? So in general, it's a two-body potential, although the form might not be a simple Coulomb one. But you see, it's the same story, okay? So this object is summed over all pairs in a very democratic way. Okay, so for that, also there is a second quantization prescription. So in second quantization, the object this time involves not 2, but 4 labels, okay? So let me just write it as, well, there is a 1/2, then there is a sum over alpha 1 and alpha 2, alpha 1 prime and alpha 2 prime. Then there is an A dagger, A. So say this is alpha 1, this is alpha 2, this is alpha 1 prime, and this is alpha 2 prime. And here you have a matrix element of the object that you have here or here. So let's call it V, okay? In between the state alpha 1, alpha 2 on the right, and alpha 1 prime, alpha 2 prime on the left, where by definition, and this has to be very carefully considered, the index 1 here is related to the same particle, and here the index 2 is related to the same particle, okay? You can always change your convention, but careful. The order here is with the two indices related to the same particle close by, okay? So not like this. If you write it like this, okay, it would be possibly wrong for fermions by a minus sign, okay? So you have to match the convention you use here with the convention you use there, okay? So use whatever letters you want, alpha, beta, whatever, but always have clear in mind that this matrix element here, okay, has the form of a double integral where the variable here and here act on the same particle, say particle 1, and the variable here and there also act on the same particle, say particle 2, okay? For these objects, the same comment regarding spin applies, okay? A typical Coulomb interaction potential or other form of potential do not involve the spin, okay? And therefore, the spin of this and the spin of this are the same. And similarly, the spin of alpha 2 and the spin of alpha 2 prime are the same, okay? So if I make the spin explicit, I should write something like here, a sigma 1, so this is the orbital part and this is the spin. This is the orbital part and this is the spin. This spin here would be the same, okay? So the orbital part in general can change, but the spin would be the same. And here the same. The orbital part can change, but the spin would be the same, okay? At this point, these are just orbital part labels. However, I should add also a sum over the two indices of spin, sigma 1 and sigma 2, Okay? So this would be a more detailed expression for the Coulomb interaction or any other potential that does not depend on spin in second quantization. Okay? Now, what I want to do with you, it's a kind of exercise, but I think it's physically very, very interesting. And it's the following. Suppose that you have some atom, an atom, for instance, or a more general system, but suppose it's an atom. And you have a Hamiltonian. You have a Hamiltonian that is the sum of some one-body terms. For instance, you have, the potential of the nucleus, for instance, or some other mean field prescription, which is, however, sum over I from 1 to n of H0I, okay, plus Coulomb interaction, okay? I'm writing for you now a first quantization Hamiltonian, okay? Suppose that you have in some way solved by just finding the levels of H0. You have solved the level of H0, okay? So here they are. I draw them as if they were hydrogen-like. They are probably a little bit changed if you modify a bit the Hamiltonian with some mean field effective, but it doesn't matter. It's essentially hydrogen-like, so there is a 1s level. Okay, I draw two of them because it's a spin. Then there is a 2s level. There will be a 2p level. For hydrogen would be exactly degenerate with the 2p, like this. But we know that due to different things, including possibly spin orbit effect, but mainly due to the fact that the potential is not, strictly speaking, 1 over r in any atom, which is not an atom with a single electron. In any mean field type of thing, you will find perhaps that 2p level would be slightly higher, for instance, than the 2s, okay? In any case, this is not central to what I'm saying, just to warn you that the exact degeneracy is there only for a strict 1 over r potential, okay? So as soon as you think of some Hamiltonian with some external potential of any type, which is not a strict 1 over r, that thing is lost, okay? Then there would be 3s, 3p, perhaps 3d, and once again, not necessarily degenerate with 3d. Okay? So, let's see. I have a second quantization description. And for instance, this thing here would be sum over alpha and alpha prime. The spin is perhaps not involved in H0. Suppose that H0 doesn't depend on spin, okay? So there is a sum over sigma as well. And in the spirit of what I've written here, I would have the matrix element of H0 in between alpha and alpha prime. And then I would have A dagger alpha prime sigma A alpha sigma, okay? Alpha and alpha prime are just orbital part of quantum number, okay? On the contrary, this would have exactly this look, okay? I do not rewrite it again. The matrix element that I have here, for completeness, is simply the integral over the two variables, the R1, the R2, of E squared over R1 minus R2. And you see, this is phi alpha 1 of particle 1, okay? This is phi alpha 2 of particle 2. And then, careful, alpha 1 prime is associated to particle 1. So I should write phi star R1 okay, alpha 1 prime, and not R2, okay? And phi star alpha 2 prime R2, okay? So this would be the integral, a double integral, so a 6-dimensional integral that you need to calculate. Now, in fact, for hydrogen-like orbitals, like spherical harmonics times exponential, they're called Slater orbitals, these integrals are calculable, and in fact, they are very well known. They're written even in books, okay? So, I mean, things are very well under control, so they can be calculated and everything. Okay, so this is in second quantization, the effect of the Coulomb interaction. Now, suppose that I have selected the alpha, the basis, to be the basis that diagonalize H0, okay? So alpha diagonalizes H0. This means that here, alpha and alpha prime have to be the same, because these are eigenstates, okay? So this object here is equal to the energy, okay, of the state alpha times delta alpha alpha prime, where the epsilon alpha is what I'm drawing here, okay? Is this clear? Okay. At this point, this becomes a very simple Hamiltonian. So this is perfectly diagonal, sum over sigma, sum over alpha, then epsilon alpha, and then essentially n, the operator that counts alpha sigma, okay? So if there is an electron in the orbital alpha sigma, then this contributes an energy epsilon alpha, depending where the electron is. If it is here, okay, you pay epsilon 1s. If it is there, you pay epsilon 2p, okay? And you sum, okay? So this is very simple. If you neglect Coulomb interaction altogether, and I give you a single state, okay, so for instance an electron here, an electron here, an electron there, and an electron there, and I ask you what is the energy, well, you can say two things. This is an eigenstate, okay? Because after all, the Hamiltonian is just sum over n particle occupation. There is nothing that changes the state. Therefore, it is an eigenstate, and the associated energy is epsilon 1s plus epsilon 2p plus epsilon 3p plus epsilon 3d, for instance, okay? So you can calculate the energy. Particularly, if I ask you, suppose that I have 6 electrons. What is the ground state for 6 electrons? Well, you just you try to minimize the epsilon, okay? So you first use this, then you use this, okay? So you put an electron in 1s up, 1s down. This is what we did for helium, if you remember, okay? Then you go on, the other 2 you put it there, okay? And then you have 2 electrons that you can put there, okay? In any of the states, in fact, you have some arbitrariness. It doesn't matter. They all cost epsilon 2p and epsilon 2p, okay? This would be the best you can do at the level of the single particle, the one-body term, obviously. You try to minimize according to Pauli principle. And that's what you always use when you do chemistry with the boxes, okay? You draw levels, and you start filling the boxes, okay, with up and down. The idea is neglect Coulomb interaction, please. Just try to fill the boxes. Now, Coulomb interaction is not small at all. We saw last time, okay, the order of magnitude for helium of the matrix element that how much energy these two guys pay in staying in the same orbital, the same physical orbital. They pay more than 30 electron volt of energy, of Coulomb repulsion. However, this is somehow tolerable if the energy cost to promote an electron from here to there, it's even bigger than that, okay? So you pay a price for that staying together in the same orbital, but you gain a lot. You gain you gain more, in fact, because if you take this element and you put it there, you have to pay this tremendous energy, which if you calculate is more than that, is more than what you pay, okay? So in some sense, there is a compromise that the system does in trying to minimize Coulomb interaction. I mean, I don't mean that the whole state is the two electrons there. There are some components of the states when you expand in this basis where the state is also a little bit in the excited states, but there is only a fraction of amplitude. Most of it is there, although Coulomb interaction is not small at all, okay? But whenever you have many choices, okay, for instance, here there was no choice. If you just don't do that, you have to pay a lot. But here, for instance, you can have several choices. You have to put 2 electrons into 6 states. 3 of them are up and 3 of them are down. They cost the same energy, epsilon 2p. The question, where do you put them? Okay? And you notice that the question, where do you put them, implies a lot in terms of spin. For instance, if you put it both up or both down, the resulting spin, okay, well, there is one thing that I just tell you. It's simple to verify, but I have not done it, is that these 2 things are in a singlet, okay? And this we have done. But even when you put this and this 2, okay, this is still a singlet, okay? In other words, the state in which I have A dagger 1s up, A dagger 1s down, okay? This is this later determinant we use for helium. Then I have A dagger 2s up, A dagger, well, say, let's use the same convention, up before down, okay? Even the order of up and down is important. You select once and for all, okay, if you have to calculate matrix element. Okay, so suppose that you order in this way. It's arbitrary. Okay, this would be this piece of state. This is a singlet, because this is a singlet, this is a singlet, 2 singlets together to spin 0, just form a spin 0. So believe me, you can be verified. I mean, you should, in principle, write the spin operator in second quantization and work a little bit and prove that this is a spin 0, okay? If I have time, maybe I will tell you how to do this kind of calculations. But nevertheless, believe me, this is a singlet. Now, if you put the 2p both up, so A dagger 2p up and A dagger 2p up, you can do that because there are several 2p. So one, let's be more explicit. One is, for instance, the 2, 1, I don't know, 1, and the other would be the 2, 1, 0, for instance, or the 2, 1, minus 1. Okay, there are 3 states, and therefore you can put 2 spin up there, okay, in these 3 boxes. Where is it? Here. These are the up boxes. You can put 2 of them in any of the 3 slots. Well, quite clearly, this is a spin 1 state. Okay? 2 spin up. And there are 2 partners of this triplet. Up, up, down, down, and up, down, plus down, up. Okay? So there are 3 states, actually, all triplet, which are formed by putting the 2 electrons there, the 2 electrons there, or 1 there, plus 1 there, and 1 there in the opposite. I mean, there is a way of writing triplet. I will show it in a second. Okay? So in some sense, the question, where do you put the electron, has implication on what will be the resulting spin of the state. And notice that spin at this level has played no role in the matrix element except for being conserved, okay? So what I said is that one body does not involve the spin, so the spin you destroy and the spin you create are the same, okay? These levels are totally spin degenerate, so spin has played a very minor role in some sense, but it's there, okay? It is there in the description of the Hilbert space. And because of that, in some occasions, it appears and say, hey, I am there. You have to respect me. You have to account for me, okay? And here will be a case in which we will discover that Coulomb interaction prefers that you put the 2 electrons in spin 1 rather than, for instance, in a spin 0 state, okay? Now, this is called exchange, okay? This is due to exchange. Another name for this physics is Hund's rule. Maybe you have heard of them. This is in particular the first Hund's rule, okay? If you have degenerate orbitals, degenerate atomic orbitals, then the thing you have to try to do is to maximize the spin, okay, rather than putting the electron wherever you want. You have to try to maximize the spin. That's what Hund suggests. Then there are second Hund's rule and so on to maximize angular momentum, but that's the most important one, okay? So that's the reason why many atoms, okay, when isolated in low temperature, they would be magnetic, okay? Although in principle, they have the chance of being non-magnetic. For instance, they could form a singlet. Carbon, for instance, could form a singlet, okay, by putting these 2 p electrons up and down, minus down, up. But it doesn't. It prefers triplet, okay? So that is somehow physics, okay? And this is all due to Coulomb interactions and to the presence of spin. Although spin doesn't play any other role. There is no magnetic field that splits the levels, nothing, okay? It's simply there and simply contributes to degenerate states, and that's enough, plus Coulomb interaction, to stabilize high spin and therefore magnetic configuration. Now, I don't want to do for you, it could be done, okay? The full calculation here, because after all, I might try to do some perturbation theory now, okay? So you realize that if I put the first 2 electrons there, the second 2 electrons there, and I have 6 electrons, for instance, carbon, then the next 2 electrons should go in the 2p states, and I have a degenerate number of levels in which I can put these 2 electrons, and therefore I can play degenerate perturbation theory and write the matrix. What is the perturbation operator? Coulomb interaction, okay? So I write the matrix where I calculate the expectation value of Coulomb interaction between all these states that I can choose. Well, the number of states is, I mean, remember, 6 boxes, 2 things. So it is 6 over 2, okay? So it's not small, but in principle can be managed. And you can write all matrix element of the Coulomb interaction in between all these states that you can write, diagonalize, and find out what is the resulting best state, okay? Now, this requires a longer exercise, and I don't want to adventure in it. Would be perhaps too much. I want to do a simpler. So suppose that I truncate, and rather than 2, I have 4. Rather than 3, I have 2 states, okay? So the 2 states, let me call it 1 and 2, okay? Could be up or down, okay? So the exercise is the following. Assume that all the other electrons stay frozen in whatever orbitals they are. And there are only 2 remaining electrons to be placed. But there is some choice in the 2 remaining electrons, and you can put it in any of the 4 orbitals that I have drawn there. So it could be orbital 1 up, orbital 2 up, or orbital 1 down, or orbital 2 down. Okay? So you have 4 choices, and you have to put only 2. Question, what is the solution that minimizes Coulomb interaction? That is what I'm trying to do now for you. Okay? Let's see if I can do that. Okay. So the Coulomb interaction has essentially all indices there. However, I do pretend that everything else is frozen. So I want just to keep track of these 2 levels, okay? So what I'm going to do is to neglect all other parts of the Coulomb interaction except those in which alpha 1 and alpha 2 and alpha 1 prime and alpha 2 prime are just the relevant orbitals that I call 1 and 2, okay? So in some sense now I have only two possible terms. I have a term that is okay, I have a term that is essentially, so let me say the relevant Coulomb interaction. It is equal to this object being, say, 1, so A1 sigma, or sigma 1, A2 sigma 2, and then I can create it in two possible ways. I can just create this in 1 again, and I create this in 2, or the opposite. So there is another piece that is A dagger, A, so 1 sigma 1, 2 sigma 2, and I create in the opposite way. So 2 sigma 1 and 1 sigma 2, okay? The spin has to be conserved always, okay? But the orbital part, okay, in general is free, okay? I am summing over all possible, okay? I have only two values of this thing, so alpha 1 can be only 1 and 2, and alpha 1 prime as well, but the order might be the same or exchanged, okay? And you see that there are also the terms with 2, A2 sigma 1, A1 sigma 2, and A dagger 2 sigma 1, and A dagger 1 sigma 2. In other words, these indices might be, the indices here might be just 1, 2, or 2, 1, and then again 2, 1, okay? So you see pretty much the same term as before, and you realize that the matrix element must be the same. This object here has a matrix element that is V, 1, 2, and then 1, 2, okay? So the orbital is exactly the same, and this is a matrix element 2, 1, and 2, 1. So again, 2 with 2. So you realize that the matrix element is identical, right? Because it's an integral in which I just have changed. So the first would be here I have 1, and here I have 2, and here I have 1, and here I have 2. And the other is I have 2 here, 1 here, 2 here, and 1 here. Doesn't make any difference because you just change the label R1 with R2. They are just integration variables. The potential is symmetric under R1 and R2, and obviously the result is identical. So this integral and this integral are the same, and because of that, there is no need to keep actually this term here, okay? You can just keep this one with a factor 2, essentially, and you cancel this, okay? So it is totally equivalent to essentially writing only the first one. Sorry, I write the first one. So I have here V1, 2, 1, 2, and no factor 1/2 in front, and I erase this. Okay? In a similar way, the second term also appears not only in this way, but it appears also in the possible other choice, 2, 1, 1, 2. Okay? But once again, the two matrix elements are related by an obvious change of variable. Okay? So there is no need to account for both, just account one. One thing that you might say, okay, why? Correct, the matrix element is the same, but the term seems to be different, right? I mean, after all, the second term here, I write it again before I forget this comment. It looks like this, okay? A dagger 2 sigma 1, A dagger 1 sigma 2. So the matrix element I discussed before can be taken to be just the same. But you might be worried and say, why you just canceled the factor 1/2 there, and when the term is actually different? Well, it's different, but trivially different. You can commute these two things, and you get this. You commute these two, and you get that, okay? And therefore, essentially, you have the same thing. You might say, hey, I don't have the same thing, because if I commute, I get A dagger 2 sigma 2, okay? So let me do the steps. If I commute these two, I get A dagger 2 sigma 1, A dagger 1 sigma 2, A 1 sigma 2, A 2 sigma 1, okay? Notice I do not pay any minus sign because I have two minus signs, okay? So I can do that. However, the things depend on the spin now in the opposite way, right? But there is a sum over sigma 1 and sigma 2 that I always have to admit in front. Remember? There is a sum. And therefore, you can also change the name of what is sigma 2 and what is sigma 1, okay? So in a sense, not only the matrix element is the same, but the two operators are really the same, and this simply cancels the factor 1/2, okay? So to make life easier, I just write it like this. Sum over sigma 1, sigma 2 of the matrix element 2, 1, 1, 2 times that term there, okay? Now, the second one, by similar reasoning, again, you can cancel the factor 1/2. You have to have a sum over sigma 1 and sigma 2. You have now the index 1, 2, and the other 2, 1, so exchanged. And here, the matrix element is also exchanged. Okay? And this is all of the relevant Coulomb interaction, because again, I want all the indices to run into this interesting subspace of 1 and 2, orbital 1 and orbital 2, okay? Now, one comment. You immediately see that, for instance, let us consider the first matrix element, okay? So V 1, 2, 1, 2, okay? So 1 goes into 1 and 2 into 2. You see? 1 into 1 and 2 into 2. Now, if 1 goes into 1, this is simply phi 1 R1 modulo square. Okay? So I can rewrite this as integral of phi 1 R1 modulo square E square over R1 minus R2 phi 2 star, R2 modulo square. Okay? So this is an obvious interaction between the two charge distribution in orbital 1 and in orbital 2. Okay? So this is exactly what classically the two charge distribution would cost. All right. Okay, so this is in some sense classically simple. It's called direct Coulomb term, direct Coulomb matrix element. Direct in the sense that it's just a direct interaction between the two orbitals. And also to distinguish it from the next one that is called exchange Coulomb term. Why exchange? Well, by the very simple meaning of the name. I have 1 and 2 on the right, and the exchange configuration, so 2 and 1 on the left. Okay? This implies, again, a double integral. Okay? Now, let me write it. E square over R1 minus R2. So on the right, I have the same thing. So phi 1 R1, phi 2 R2. On the left, however, 1 goes into orbital 2. So phi 2 star is associated to still R1, and phi 1 star is associated to R2. You see the difference? It's a crucial difference. R1, R1, R2, R2. But now, here I have a 2 rather than 1. And therefore, this is no longer the modulus square of phi 1. And this is no longer the modulus square of phi 2. Okay? So, this object here is not, I mean, it's called exchange just because of this. Because the thing that we have here, you just exchange it. And it's not obvious Coulomb interaction. Well, you might even question, I mean, it's obvious that this thing here is positive, 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 is a positive thing, okay? So this is a repulsive interaction, so this is certainly greater than 0. Now, the object that you have there, you can write in the following way. Call this object rho. Rho of R1. Okay? So let me write it. Integral in dR1, dR2. You see I have E squared over R1 minus R2. Then I have rho of R1. And what is this remaining thing? Well, is the star of rho evaluated at R2. Rho star R2. Okay? So this looks a kind of self-interaction, however, of a charge distribution ρ that is in general complex. Okay? Now, you might even question, will this be real or not? Will it be positive or negative if it is real? Well, you can show, and it's pretty simple to show, that this term here is real and positive. Okay? Although it's less trivial than this. This, you just look at, everything is real, everything is positive, integral must be positive. Here, this is positive, but this is a complex quantity in general, times its star, okay? So it's the self-interaction of a kind of complex charge distribution. Nevertheless, you can prove that this is still real. Real and positive. The way you prove it is the following. If you look at this object, you see that it is a convolution. Write this as integral in dR2, and then I have here an integral in dR1, okay, of this. So you see, essentially, that is, this object is a convolution. You see? Because it's an integral of function of R1 minus R2 times function of R1. Okay? So an object like this is nicely analyzed in Fourier. Okay? You know that convolutions become simple in Fourier space. In other words, you can verify, and this is not very difficult to actually calculate it, that if you introduce the Fourier transform of each single term there, okay, so you go from R to K space, you know that the Fourier transform of the Coulomb potential, for instance, can be calculated, and is simply 4 pi. So the Fourier transform of this is 4 pi E squared over K squared. Okay? And you introduce also the Fourier transform of the rho. You can prove very easily, and do it as an exercise, that this is equal to, just get some space. So exercise for you, introduce Fourier transform of each quantity, to, using the fact that the Fourier transform of the Coulomb is this, to show that this object is the integral over dk of 4 pi E squared over K squared times rho K times rho K star, so the modulus square of rho K. okay? But this is the Fourier transform of rho r. Please do it. It's very simple. Just introduce Fourier transform and use the fact that in some sense you have convolutions. And this is the result, okay? So no matter what the charge distribution is, even complex, the self-interaction of it is a real positive quantity, okay? That is important in the discussion that follows, okay? So the two integrals are both real and positive, and they can be calculated, by the way, using the standard form, for instance, of hydrogen-like orbitals, if you have hydrogen-like orbitals, okay? They are tabulated and everything. But for our reasoning, it doesn't matter what they are. It's important that this is, I call it V12, okay, is the direct Coulomb interaction between orbital 1 and orbital 2, okay? Let me just give it a name here, V12. And this object here is called J12, is an exchange Coulomb interaction, okay, where the other two indices have been exchanged, and is called usually J12, okay? So J12 is also real and positive. Okay, good. Armed with this, we proceed now. Do you have questions until now? So, everything regarding one body is fixed. I mean, I'm not questioning it. Everything is fixed until here, and I have simply to take care of the possible way of putting the two electrons in this four-dimensional space, okay? So I neglect altogether all other A dagger, and I only consider the four possible states that I can have. Let's see what they are. Now, state number one is putting an electron in orbital 1 up, orbital 2 up. Okay? The other electrons, since I will never touch them with Coulomb interaction, nothing, I consider them frozen, I even forget about them. Okay? They are there if you want, okay? You can write them, but they are always there, not touched, not acted upon. Okay? Good. So this is the state in which I put, for instance, the two electrons like here, and here, up. Okay? Then there is an obvious partner where I put the two electrons down. So psi, let me call it 4 rather than 2, which is A dagger 1 down, A dagger 2 down. Okay? Good. What other states you can form? Well, you can form certainly the following state. Psi 2, you put the electron in 1 down here and in 2 up. Okay? So like this. So A dagger 1 down, A dagger 2 up. Okay? And notice that I have decided an arbitrary ordering. So I decide to put the 1 always before the 2. Okay? And this is, therefore, the result. And psi 3, I put still the 1 before the 2, but now the 1 is up and the 2 is down. Okay? So these are the 4 possible states that I can form by putting the 2 balls in the 4 boxes. Okay? 2 electrons in 4 possible states. They all cost the same one particle energy, which is 2 epsilon 1 plus epsilon 2, which is degenerate. Okay? Now, let us solve the problem of finding the 4x4 matrix, okay, that Coulomb interaction generates. Okay? So in principle, what I should do is the following. I should try to act with this Coulomb interaction, okay, the relevant parts, this on, for instance, on the state psi 1. and then see what I get, then do it on the state psi2 and see what I get, and so on and so forth. And then I will be able to write the matrix, okay? In general, the matrix would be a 4x4 matrix, okay? Where in each element I will have psi I v Coulomb, psi j, okay? This is generic ij element, okay? So the 1, 1, 1, 2, 1, 3, 1, 4, and so forth. 16 elements in principle, okay? So let's us try to do. Let's see. Let's do the, this is an exercise in manipulating A and A dagger, essentially, okay? Now, for instance, 1. 1 is 2 electrons up in 1 and 2. So obviously, sigma 1 and sigma 2 have to be both up, because I want to destroy 1 up and 2 up, okay? So you have to take this to be up. Otherwise, I cannot destroy the down, in other words, because in 1, 2 there is no, okay? I'm looking at this, okay? So for psi 1, I need to invoke, maybe I should not erase this, otherwise for the next calculation I would be, okay? So the term that destroys this is 1 up, 1 down. A 1 up, A, sorry, 2 up. Then obviously I have to create again the 1 up and again the 2 up. And the matrix element I know it's called V12, okay? V12. So this certainly destroys the state psi 1 and creates what? Psi 1, exactly the same. In essence, this really is a number operator. It counts, you see? And this is also a number. So this is n1 up, n2 up. So it simply, you simply recover the same state, okay? So this thing will be just V12 times the same state, at least for this first piece. What about the second piece? The second piece, you have to be a little bit careful. Now I have here, again, this has to be up and this has to be up because you want to destroy the 1 up, 2 up, okay? However, if you do so, then you have now A dagger 2 up, A dagger 1 up. And here I have J12, okay? Now, careful. If I apply this, let's do it carefully because now there is a surprise, a minus sign. And therefore I want to show it to you very, very carefully. So I do have this term, okay? So I have J12, A dagger, A, where I have 1 up, 2 up, 2 up, 1 up. And I must act on psi 1, that is A dagger 1 up, A dagger 2 up, 0. Okay, so this is psi 1, and this is the piece of Coulomb interaction that is on second line. Okay, the only relevant one, however, the one in which sigma 1 and sigma 2 are both up. Okay, there it is. Okay, now let us do the exercise. You can essentially bring this, okay, there, okay, and if you bring it there, then creating and immediately destroying the thing is essentially total cancellation of the effect you do. However, in order to bring this over that, okay, you remember that the two operators, for instance, if you have A1 up, A2 up, you will have a delta, but the delta is just 0 because the two indices are the same. So the two anti-commute. And therefore, in doing this, you get a minus sign. Okay? So let me do the steps. You get the first minus sign. Then I have A dagger 1 up, A dagger 2 up. then I have A 1 up, then I have A dagger 1 up, and then I have this guy that has gone there. So A 2 up, A dagger 2 up. Okay? I have simply anti-commuted those two terms and paid the minus sign. Now, this, they cancel. You create and you immediately destroy. Okay? No effect. Now you have creation and immediate destruction of 1. Okay? So once again, these two cancel. No effect. So the only remaining guys are these two creation operators, which in the end reconstruct exactly psi 1. You see? However, minus sign. Okay? So the result is that this is minus J12 psi 1. Okay? This minus sign is very important. I told you that this and this are both real and positive. Okay? So the effect of this is V12 minus J12 psi 1. Okay? So psi 1 somehow is favored a little bit, we'll see in a second, with respect to other things, because of this minus sign. Okay? Wait a second and everything will be clear. Let us, so the first element, the first row really is just one element. You see that 1 goes into itself. So here I have V12 minus J12, and then I have 0, 0, 0, 0, 0, 0. Okay? Then let's see the fourth, the last one. Well, perhaps it's no surprise that if you consider the fourth, you will have exactly the same result. Okay? I'll do it for you now rather shortly. Okay? So you will have exactly V12 minus J12. Okay? And 0, 0, 0, 0 here. Okay? The reason is very simple. The only thing that changes with respect to the algebra I did before is that what was here up now will be totally down. So for instance, let us consider the second, the exchange one. I would have here one one down, two down. And here I have one down, two down, two down, one down. Okay? But, I mean, everything is exactly, I mean, just change every up into a down, and you will see that nothing really changes with respect to the previous algebra. So certainly this is minus psi 4. And even the first term, you see it's exactly psi 4 with a plus V12. So it's the same algebra as before. Good. So 1 and 4 are already eigenstates. And they have this energy. Okay? Perhaps it's not surprised that they are eigenstates. I mean, somehow they are spin eigenstates also. V doesn't change the potential, doesn't change the spin, and therefore they cannot be mixed to anything else because they have spin 1 and total component of the spin plus 1. They are the only state with that. The spin would never change this, and therefore it must be an eigenstate. Okay? By the same reasoning, these are also spin 1 and total component minus 1. The spin is not changed, and therefore this is the only state, in other words, that has that spin. Yeah. What? Where? Here? Is it clear? Is it clear that here there is a plus, and this matrix element here is J? So this is V12, and this is J12, and they are both with a plus. This is clear, right? Okay. Now, let us do the problem I've written here. Psi 4, okay, is this state. You see, read it from here, down, down. okay? And this term here would be 1, 2, 1, 2, then 2, 1, 2, 1, okay? And in order, if I use sigma 1 and sigma 2 different from down, down, I would certainly get 0 because I cannot destroy an up on a state which has no up, okay? Good. So I have to take all of them to be down, okay? Now, you ask why there is a minus. Well, there is a minus in essence because in order to destroy this particle 2 down that I have created here, I have to have this object acting on the state. But you see, to have it act in a natural way, it has to be just close to the creation operator. And in order to bring this into this form, so the 2 and the 1 exchanged, so you see I have exchanged this 2, I have to pay a minus sign because 1 and 2 always anti-commute, okay? So I can write this into the exchanged form with a minus sign. Now, once I have written it in this way, I have 2, 2, creation and destruction. 1, 1, creation and destruction. They have no effect, therefore. But in order to have in this nice form, I need an exchange before. Okay? Good. So let us finish now the exercise by calculating the most complicated pieces. That is, for instance, let us act on the state, for instance, 2, down, up, okay? Psi 2, which is the 1 down, 2 up, okay? So I have 2 terms to consider. Let's see, I write it here. Psi 2 is I dagger 1 down, A dagger 2 up, okay? This is this psi 2. Let's see what I have there. There are 2 possible things. One is this one. So I have A1, A2, sigma 1, sigma 2. Then I have A dagger 1, sigma 1, A dagger 2, sigma 2, V1, 2, and I have to sum over sigma 1 and sigma 2. So tell me what sigma 1 and sigma 2 you would choose. I'm making the exercise a little bit, I don't do it myself. I ask you a little bit of advice. Okay, I have a 1 down and a 2 up. I want to destroy them, okay? And I want to destroy this. Otherwise, if I don't destroy this, I get the vacuum, and therefore the A just gives you 0, okay? So the only way you don't get 0 immediately is if this destroys that, and this destroys that, okay? So what choice would you make? This equal to down, good. And this equal to up, good. Okay, fantastic. Then this fixes this to be down and this to be up. Okay, do we agree? And there is no longer a sum because I have selected the only possible term. Okay, good. So let us do the exercise. In order to apply the same thing we did before, I should bring this there, okay? This costs a minus sign. Good, minus 1. Good, let's do it. So this is minus V1, 2, A dagger 2 up, A dagger 1 down. And then I have A1 down, A dagger 1 down, and now A2 up, A dagger 2 up, vacuum. Okay? I've paid my minus sign, and now they are in this form. So 2 destroys the immediate creation of 2, they go. 1 destroys the freshly created 1, they go. Okay? And you have that state. What is it? What state is this? Huh? it is, no, it's not psi 4 because it's up, down. It's psi 2, but not quite psi 2. It's minus psi 2 because psi 2 has the opposite order, and this is your question. The order is important, okay? So I have to pay another minus sign in order to exchange these two, okay? And I write it plus V12 A dagger 1 down, A dagger 2 up, vacuum. In this form, it's perfectly psi 2, okay? So this is equal to V12 psi 2, okay? Good. This is the first piece. Second piece, okay? The second piece would be this, okay? So J12, let's do the algebra, completely copied so that you help me again in determining everything. Otherwise, I finish doing everything and maybe things are not clear. So the state is still psi 2, therefore A dagger 1 down, A dagger 2 up, vacuum, okay? So let's see. I want to destroy things, and I want to destroy these two things. Otherwise, there is a 0. So let's see. 1 has to be down, as before. 2 has to be up. Okay? This fixes immediately this to be down, and this to be up. And there is no longer any need for a sum. The other terms are 0. Good. Okay. Usual thing. Pay a price. Bring this there. Okay? So minus J12, A dagger 1 up, A dagger 2 down, one down, A dagger 1 down, A2 up, A dagger 2 up, vacuum. Create and destroy 2 up. There you go. Create and destroy 1 down. There you go. The remaining thing is, however, not psi 2, but is psi 3. Okay? Good. So this thing is really equal to minus J12 psi 3. Okay? Good. So I have written that psi Coulomb applied to psi 2 is equal to V12 psi 2 minus J12 psi 3. Okay? So now 2 is mixed to 3. Before 1 was alone, 4 was alone. Now 2 is mixed to 3. And you can verify, it's very, very simple, that 3 is also mixed to 2, obviously. So in some sense, once I have here the fact that here I must have V12, and here I must have, let's see, minus the element 2, 3. In some sense, what I have already determined is the fact that the element, this is V12 and this is J12, right? And you will realize that by necessity, here you must have minus J12 because this operator is Hermitian, and you can verify that indeed you have here V12 psi 3 minus J12 psi 2. Okay? I don't do the algebra explicitly, but it's very, very, very analogous to this. Okay? So look at what you have for this 4-dimensional matrix. You have a block 2 by 2 in the middle, formed by the state 2 and 3, which are mixed together. Coulomb interaction mixes 2 and 3, while Coulomb interaction leaves 1 and 4 untouched. Now, can you tell me, when you have a matrix like this, how do you diagonalize it? It's the typical 2 by 2 problem, right? You have probably done many times for tight binding of 2 orbitals. Okay, there are 2 eigenstates. One is the sum and one is the difference of psi 2 and psi 3 with the square root of 2 factor, okay? The sum gets energy which is, you can verify that the element psi 2 plus psi 3 over square root of 2 will have an energy that is V12 minus J12. The other, which is the difference, will have an energy that is V12 plus J12. Okay? So notice, this term is exactly the same energy as these two guys. In fact, you can prove and you can verify very easily that this is the other member of the triplet multiplet. Okay? One is up, up, the other is down, down. The third combination is this plus that. So a dagger, 1 up, one up, a dagger, 2 down, plus a dagger, 1 down, a dagger, 2 up. Okay? So this is the element that is written there. Okay? Up, down, plus down, up. It's the third element of the triplet. So this is a spin S equal 1, Sz equal 0. While this is spin 1, Sz equal 1. And this is spin 1, Sz equal to minus 1. Okay? So here are the three elements of the triplet. 1, 2, and the sum of these two. The other guy, the one with the minus, is the singlet. Okay? S equals 0, Sz equals 0 is 1 over root 2, a dagger, let's see. Well, it doesn't matter if it is a singlet or minus the singlet. So let me write it as 1 up, a dagger 2 down, minus a dagger 1 down, a dagger 2 up. Okay? This is essentially, it would be psi 3 minus psi 2. Okay? The combination with the minus. You can always change sign globally to a state, okay? So this state and that state that I have written there, which differ by a global minus sign, are exactly the same, okay? Good. So Coulomb interaction tells you that the 4 states that you can form are actually the following. A triplet, okay, which has energy V12 minus J12, V12 minus J12, V12 minus J12, and a poor guy, singlet, V12 plus J12. You see that being these two objects, elements that are both positive, the triplet gains. It reduces the direct Coulomb energy by the exchange one. On the contrary, the singlet has increased its energy. Okay? So if you measure the splitting between the triplet and the singlet, okay, so the state, rather than being perfectly democratic, will be actually the 3 triplets being brought down and the other singlet being brought up, and the difference between them is twice J12. Okay? So you see that the system, by Coulomb interaction, tries to make the triplet preferred, while the singlet is definitely disfavored. Okay? And this is all a magic of Coulomb and spin being simply present. There is no other magnetic term. There is no magnetic field, nothing. Okay? Simply Coulomb interaction is able to provide magnetism. This is very important. In some sense, to have magnetism, you do not necessarily have some external field that tells the system, please magnetize. Okay? The system by itself can prefer being magnetic. Okay? This is quite intriguing, okay? So magnetism sometimes spontaneously arises because that's better, okay, energetically, okay? I find this quite instructive, okay? And also it's a nice exercise of second quantization where you see exactly, you have always to be careful when you anti-commute fermions, the order you give to the states and things like this, the minus signs that you need. You realize this is, again, a two-particle exercise. I might have done the whole thing in first quantization. It would have taken very little effort to do it in first quantization. But imagine doing real calculation with more than two particles or with more than two orbitals. I mean, with this technique, everything reduces to jumping and counting minus signs. The other is a tremendous mess, sum over permutations, things like this, okay? So this is necessarily what you need to do when you have to do an actual calculation, okay? So even systems which are formulated in first quantization, the first thing you try to do is, let me write it in second quantization, okay? Because you certainly gain. You do a little bit of initial setting, but once you have set the thing, the calculation in second quantization is usually simpler, okay? Okay, so I would, well, I think I will stop here. It's a natural break.